Well, hey everybody, welcome back to Old School Math. Today we're going to talk about linear programming. Now, linear programming is a term that might intimidate you, but there's no programming involved in it. It's just a statement, or it's just a phrase that says we're going to take some things that we've learned with linear equations and linear inequalities and systems of equations, and we're going to put those together in a word problem in order to maximize or minimize or find the best optimal solution for an example here. We're going to look at popcorn and snacks that are, or popcorn and sodas that are sold during an intermission. To stay in business, it must sell at least 5 popcorns, but no more than 25. It must also sell at least 20 sodas, but no more than 50. The snack bar cannot sell more than 50 items total during the intermission. The profit for popcorn is $1.50 per box, and for soda is 25 cents per can. How many of each item should the snack bar sell to maximize their profit? So if you're selling anything, that's obviously your objective, right? To make the most money possible. And if we think about something like an intermission, there's going to be some constraints here, right? So at least 5 popcorns, but no more than 25. And at least 20 sodas, but no more than 50. If we think about why we might want to set these constraints in a situation like this, why wouldn't you say, well, let's just sell 25 popcorns and 50 sodas? Intermissions are timed, so they might have an idea that we can only serve a certain number of people in this time. We might have constraints with how much our popcorn machine can actually make, between 5 bags and 25 bags. And then with sodas, we know that if we don't sell the sodas, we're going to be operating at a loss. So that's really what we're looking at here, right? We're going to try and maximize the profits so that we're not wasting our materials, our popcorns and our sodas, but that we're making as much money as possible for whatever production that we're putting on here. Question A says to identify the constraints for the scenario. And it says go ahead and let X be the number of popcorns that you sold and Y be the number of sodas that you sold. So in this situation here, our popcorns we know have to be between 5 and no more than 25. So if we set up an inequality for popcorn, we know that popcorn needs to be somewhere between 5 and 25. So that means it's going to look something like this. And my question for you is the less than sign appropriate, or should it be less than or equal to? In this case, since it says at least, that means we need to sell 5 popcorn. So I'm going to go ahead and put an underline under there to make that a less than or equal to sign. And it says no more than 25. So we can actually sell 25 popcorns. Let's go ahead and make that less than or equal to as well. We're going to do the same thing with the soda. It says we can sell at least 20. And we can't sell any more than 50, but we can sell 50. So let's go ahead and make that a less than or equal to as well. So these two inequalities just says, well, X is between 5 and 25, including those numbers, and Y is between 20 and 50, including those numbers as well. We're going to use this on this next page when we start to set up our graph. So after you've identified a few constraints, we're going to graph the constraints, which I'm going to write up here now. 5 is less than or equal to X is less than or equal to 25, and 20 is less than or equal to Y, which is less than or equal to 50. And I'm going to erase this down here, okay? So on our graph, we want to go ahead and do this. And our axes aren't labeled, so let's go ahead and label the axes. We know that X is the popcorn axis. And the Y-axis is sodas. Okay? Now let's go ahead and graph these here. So we know that X is between 5 and 25, and it is included, so we're going to put a solid line going through there. And then the same thing on 25. And then the Y is between 20 and 50. So
and here we'll say we've got a line going across horizontally.
At Y equals 20, and a line going horizontally at Y equals 50. We've graphed a feasible region for our constraints, but we know one other thing. The problem said that we can only sell 50 total products between popcorn and the sodas. So that would give us a third equation here. Otherwise, this would be our feasible region inside that square or rectangle. If we want to make an equation that says we can only sell a total of popcorn and sodas that's less than or equal to 50, that would look something like this. X plus Y is less than or equal to 50. So that represents the total amount of products that we can actually sell. So if we want to graph this, one thing we might want to do is just rearrange it, subtract an x from both sides. So y is less than or equal to negative x plus 50. Okay? So that's something that we can very easily come in here and graph. We've got a y-intercept at 50 and a slope of negative 1. So I'm going to go down 5 and over 5 since that's kind of how my grids are working out on here. We're going to go ahead and complete that line. Let's talk about the actual feasible region. If you've never heard the term feasible before, well, you probably have. It just means the possible or the realistic region that we're going to be looking at. So if we want to take a look at this, it says y is less than, and a less than indicates we want to shade below the line. So we're going to take all of the points on the line and we're going to shade below them. And we're going to look at the other constraints that we graphed. We said that the y values have to be between 20 and 50. Well, here's between 20 and 50. And the x values are between 5 and 25. So really, we're looking at this whole region inside this trapezoid right here. Okay? And it says identify feasible points. So when we're doing linear programming, we want to take whatever shape our graph makes, whether it's a triangle, a square, rectangle, trapezoid, any type of geometric shape, and we want to identify these points that are going to be the vertices. We don't need to identify these points along the lines. Just your extreme points are going to be the ones that you need to take a look at. So these points over here would be the point 520. This is the point 545. This is the point 2520. 2520. And this last point is the point 2525. So these are the feasible points. Okay? And this is going to be our feasible region in here, right? Determine the objective function which models the maximum profit. So when we're looking at an objective function to maximize profit, we want to go back to our original problem, which said your profit is going to be determined by the price of the popcorn and how many popcorns you sell, and the price of the sodas and how many sodas you sell. The problem said that we would make $1.50 per box of popcorn, so 1.50 times x, plus 25 cents, 0.25, times each soda that we sold. So that's our objective function, which models the maximum profit. Notice we saved that towards the very end. We wanted to do a little bit of legwork to figure out a couple points that we could test for this, okay? So part D, and this is where we're actually going to solve the problem, determine the number of popcorns and sodas that need to be sold to maximize the profit. Now we're going to use a bit of logic before we actually go ahead and start plugging these numbers in to this equation. That would make sense, right? We've got x and y values and we can just substitute those in here. And these are the only 4 points that we need to test. But I think we can work through a couple things. Since there's no negatives in here, the more popcorn and the more sodas that we sell, the better. If we look at these 2 points, notice what they have in common. They both have 5 popcorns being sold. Obviously, we're going to make more money if we sell more sodas in this second point than in this first point. So I'm not going to bother testing that first point. We know that this one's going to make more money, right? And if we compare these two, again, we've got more popcorn sold in this, or we've got the same amount of popcorn sold in both of them, but we have more soda sold in the second one. So I'm not going to bother to test that first possibility there. So we're just going to test these 2 points, 545 and 2525. Those are these 2 points on the graph. So what I'm going to do is I'm going to set up the equation down here. P equals, and I'm going to substitute that first point, 545, 1.50 times 5 plus 0.25 times 45. And at this point, you can just type that in your calculator. You can figure out that that would be a total of $18.75. Okay? And then I'm going to do the same thing for this second point right here, 25.25. So let's use that same profit equation. $1.50 times 25 popcorns plus 25 cents times 25 sodas. So what we've done in this one, we've actually traded out 20 sodas for 20 popcorns here, which seems like it would make sense. And we know that sodas are going to sell for cheaper than popcorns and we're going to make less profit. That would give us a total of $43.75. So with this data, what you could do is you could say, okay, whoever is in charge of ordering supplies for this snack bar during this intermission, you could say, hey, we can maximize our profits in this situation if we sell 25 popcorns and 25 sodas. That's not saying you will, but if we want to make the most money possible, this is what we're going to shoot for, right? So whoever is in charge of this deal, this is something that they might want to know. And I'm going to go ahead and write this out over here. 25 popcorns and 25 sodas. And I always think it's good at the end of a linear programming problem to go ahead and write this out in terms of your variables. The reason I want to do this is this goes back and it makes sense of the problems instead of just saying, oh, well, it's this point right here, 25, 25. If you give this 25 popcorns and 25 sodas, it brings relevance back to the problem that you've done. Guys, thanks for watching. We're going to do one more of these in a separate video, so be sure to check that out.